Thank you. All right, so we're going to talk about a storage security and a proposal for an open source key management block. So, with me is Andreas from Google and Chris Sabol from Google, and I'm Bryan Kelly. So let's get into it. We talked, this slide's repeated from earlier, but we know there's, impending legislation around liability for insecure devices. It's not only coming, but there's also been a lot of movement in liability for shipping insecure products. We've seen, with data loss, there's already been penalties for those found negligent in the management of storage devices that have led to data loss. So it's not going to come as new news, but it just highlights the importance of getting out in front. You're always better to work with regulation and start to self-regulate before it comes and gets imposed upon you. So the challenge we have and why we're talking about storage media today is this media itself is quite small. There's a lot of them in data centers, a lot of them in servers, and it's something that's highly portable. Storage media stores data, and the loss of that data is not good. So, with this storage media, you're not, trying to hide an elephant. It's quite small. An SSD will fit in your pocket. So, yes, we do physical protection, such as, badge readers on data centers, restricted access, lock cabinets, all of this physical access. But these devices are so plentiful and small and portable that it's just not winnable. And what all that physical access can achieve is it can prevent some capex loss of these devices walking out the door. But what it can't do is offer encryption at rest or data encryption at scale and at rest. So. Data at rest, it's critical. It's not the same as storage media. It's critical that data is encrypted in data centers. I think every cloud service provider and data center operator, pushes for data encryption at rest and having it at multiple layers and not just one encryption cycle over that data, but multiple. And that serves a couple of different purposes. And alleviates some concerns around exfiltration of the drive if it does get lost. Some of the challenges as well we'll have with that is circular economy is something that we're pushing more and more for. We all have a responsibility for sustainability. So the circular economy, Chris was just talking about ownership transfer, and that actually plays in how that works with circular economy. It's something that we all have to take into consideration with storage device. And then, of course, another challenge for storage is data sovereignty, where that data resides, and the movement of that data, and what it's allowed to do. So this is these are all maybe some of them are storage unique challenges, but that's what we're looking to address, and some of the problems too that we want to solve with this.
Thanks, Bryan. So taking it from here. So earlier today we had a presentation from Seagate, I believe, talking about circular economy, which is of course a excellent financial incentive for everyone, and of course it's connected to sustainability. This was already described. You can reharvest ferromagnetics, you can send the ASIC and the PCBA back to the supplier, etc. However, the problem is fairly complicated for CSPs, right? We cannot afford a single drive to exit our perimeter with any kind of data at risk. Data at rest being at risk of exfiltration. As drives are getting larger and larger, in the talk earlier today, there was a lot of talk about sanitization, which is something that I think we all do. But when a drive is 60 terabytes, when a drive is 30 terabytes, you start getting into the 99% success rate. It still means a lot of drives are left on the table. Purge override cannot power wash a drive. So, for example, by purge override, we mean logically writing everything on a drive. There's still blocks that are hidden, that we don't know what they are, et cetera, et cetera. So really the problem that the solution that we all seek is crypto erase, right? Everything has been encrypted with a key that then disappears. That would be a great solution. You don't have to treat each individual block. You just forget about the key. Fortunately, we don't live in that world yet, right? There's still problems. There's still things that do not work. There are still reasons that prevent companies that have a lot to lose when data is lost from turning on crypto erase. So that's the reality, right? So that's kind of the problem statement, the arc of this problem statement. Data at rest is super important. We would like to have very elegant and scalable solutions to it. We don't have it yet. So when we look at the problem of implementing a crypto in a drive and all the things that we need to look at, and essentially what we ask someone in OCP Safe to go look into and give us an audit about, we split the problem into 4 parts. First part is boot integrity, right? Is this the right drive that I bought? Does it have the right firmware that it should be running? That's kind of the problem space of root of trust. That's a common problem space to all devices, nothing special here. Then you have the problem of algorithms. How do you do symmetric data at rest cryptography, AES, XTS, or whatever you do, right? That's a fairly well understood area of the world. Then you have the problem of key management. The keys that I'm using for each individual block, namespace, lock-in range within the namespace, are they the right keys? Have they been exfiltrated? Are they easy to regenerate, rederive? Are they easy to erase? And finally, the problem of data plane. Inside the SSD, how do we go from PCI TLPs to data at rest on media, on flash media, without leaving breadcrumbs and little pieces of plain text in places that it can be easily found? So we have Caliptra for the first problem, and that's where we're investing. We're not focusing on the symmetric encryption. That's a data path part. That's not what we're going to do here. And we're not focusing on the data plane because that is very invasive and very complicated with each individual vendor. But what we are looking at is at the problem of key quality. How do you generate keys? How do you keep them around? How do you feed them into the XTS engines for the right blocks, right? And that's a sort of like a control plane problem. If you think about an SSD ASIC, that becomes a control plane problem. So that's our focus. Well, I mean, you want to speak to this one?
I can.
Yeah, I think you should. Yeah, no, I think you should.
Okay, so then, what sort of threats, right, are we worried about here? So there's when it gets into debugging interfaces, your primary concern is I'm taking a core dump. It captures all of the relevant memory regions. There could be key areas that haven't been zeroed out. There could be just actual data that hasn't been zeroed out, unencrypted data. All these things are concerns. In terms of just general crypto key management hygiene, right? Just best practices, getting those assurances that the sequence of events to unlock a drive or to get to that key material are all using the right algorithms. And back to what Andres was saying, kind of a clean, easy to understand solution that can make us confident in those guarantees. There's firmware compromise, right? So this would be like, we're worried that if the firmware has some vulnerability in it, right? Moving data could conceivably move data between different trust domains, or access unencrypted data from hosts, surreptitiously. In terms of FIPS certification, we all know it takes quite a while to get through that, and it's basically currently part of it's all of firmware and hardware is kind of in that boundary in general, trying to minimize that boundary for FIPS certification. It also gets to the next bullet on maintainability, right? Like if we have the agility for all the NAND management and non-critical, security critical elements to be revved rapidly because it doesn't exist within that security boundary, it's a better place to be. And then, just performance is also another concern here, right? If you do go on this path of not having data encrypted wherever it's accessible, now you have to be zeroing buffers and all the threats that come along with that and the performance concerns. So like we've been saying, so the idea here is kind of build on the approach with Caliptra, right? Caliptra has both software and RTL components in there. It's the same idea here. So we're following the same open source strategy with multiple partners and a well peer-reviewed approach to solving the problem. So and along with that, just focusing on the quality of the implementation. I think also Andre sort of alluded to this. If you look at this as a data plane, which has kind of got its fingers everywhere, and key management, the idea here is to really just start with the control plane aspects and the key management portions, and to minimize disrupting the rest of an SSD architecture. So, kind of how do we look at this, right? We've already mentioned the Caliptra development model, which has these benefits of transparency. We need to worry about how many keys we support, including meeting those scalability requirements for key per namespace and strong assurances and bindings to the VF or PF level, potentially extending that to multiple bands if they're needed in some cases. I think another critical element is that root of the chain of trust for accessing the key material. So, I think we want that to be a multi-element component. So like there's a DICE alias element to that so that there's a strong locking of the root key material to the specific device. The next one kind of gets to that as well, is the option to include entropy from the other end of the stack and directly from the specific user and application. There's a need to keep all of this kind of contained within this key management block, right? So that there's no concern of leakage of key material out of there. Part of that is the vault needs to not have JTAG access to these critical elements or UART or side channel sort of vulnerabilities. The key, and the key critical key operations obviously be contained entirely within this environment. There's an element here of building on Caliptra's capabilities. I think I think we've entertained something like this in the past, but it always starts with a base of integrity, and without having Caliptra, it's sort of why are we solving this problem first? We got to solve the firmware integrity element. Yeah, and then I think also there's back to this key chain. There's a desire to potentially have like kind of host level entropy incorporated in with that as well as part of that key chain, so that we're really tying the device to the machine to the end user. And if you break that anywhere along the line, you really have to exfiltrate all of it together to get the ability to access that data. So this is kind of a very high level block diagram view. I think on the left you can kind of see a representation, a very high level representation of an SSD data path. So you've got a PCIe front end, potentially with encryption on the PCI link, but then it moves data into an unencrypted form. It moves into kind of this initial look at that command, and then into a crypto engine, right? So in that unencrypted state, we really want it. That's where we get our strong assurances of the specific port, VF, PF, that the data request is coming from, the specific namespace address, the specific LBA in question, and binding that strongly to a specific key. And then we move through the crypto engine, and you're we're sort of into this green boxes on the bottom for the rest of the data path, right? So, and this is kind of what I was alluding to with this ability to have the FIPS security boundary not include most of the elements of the SSD, especially most of the firmware elements. So to manage this data path, right? There's the block we're focused on here is this key management block, kind of in the middle of the picture, right? And so this is where keys get wrapped, unwrapped, and or derived. And it's building on the capabilities of Caliptra in terms of the firmware integrity for what's running in that key management block. And along the top, we have some of those extra operations in terms of entropy wrapping, including the host or escrowing keys and elements like that. So who are we? So there's Google, there's Microsoft. Oh, excuse me. There's Samsung and Kioxia and Solidigm. So there's 5 companies right now that are working on this project together. So to summarize this, our major goal is to increase the confidence of the encryption at rest on SSDs or storage media in general. I'm an SSD person, so I'm just going to say SSD. I mean storage device, I think. And our primary focus in that is the key management element, the key management block, right? We're going down this path of an open source block, both hardware and software, and multiple partners working together on this 5 companies I mentioned so far. And and looking for it's open source, so we're going for kind of a well peer-reviewed design. We want to with focus on the data plane. We're hoping we can have minimal disruption to the rest of SSD architectures, and it's an exciting cross-company working group that we've put together here. So I think I'm super excited about this. Yeah. What was that?
The world's our oyster.
Yes. Andre says the world's our oyster. So the call to action, so join the effort, right? We're just getting started. You can maybe see some of that from some of these high-level bullets that I'm saying. And also just join the OCP community and help us work on this. So I think that's, thank you. You want to do any questions? Yeah, I guess we have a couple minutes for questions.
Do you guys envision this requiring Caliptra or just being able to leverage Caliptra?
We're going to design it relying on the DPE interfaces that Caliptra provides.
Okay. So
Yeah.
they'll be kind of joined together.
I think so.
Yeah.
I think this is probably one of, of several blocks in the future. That's kind of like our long arc agenda. Let's start addressing the problem of consistency and security quality with open source blocks.
So the RTL then eventually, do you expect it to be available also in the CHIPS Alliance project?
I think so, right? That's, yeah.
Okay.
This model so far is working, so we'll give it more opportunities, yes.
Is there a reason why you're focusing specifically on SSD for key management? Because, key management is a very important topic, and it would be good to have some
Do you want to
standards.
take that? I think it's NVMe, the answer, right?
Yeah,
Not SSD, not storage. I'm just saying generally beyond storage as well.
It's the
money,
right? The motivation is money and data at rest. Sorry. The motivation, specifically storage motivation, is money and data at rest and liability and reputational and user confidence, right? So there's a lot of reasons to go after storage. Then there's a second level question, which is why NVMe?
right. And I in my mind, NVMe or SSD synonymous with NVMe. That's not true anymore, right? There are NVMe HDDs coming down the pipe. I think. I think this is the area where we specifically have the most concerns, right? I think there's a lot more in SaaS SATA. There's a lot more opportunity. You have, controllers and HBAs and things that have the opportunity to include additional, anyways. I think back to Andres' point, this is where we see the immediate need. I don't think there's going to be anything in the design that's, it's going to be focused on that, but I mean, that doesn't prevent somebody, it's open source, right? Somebody could take this and adapt it to some other use case. We're not planning to license this as something that you can only put in an SSD, I don't think, right? So.
SSD is a very defined use case. There are a lot of other opportunities where a hardware key block would be useful. We agree with that, but I think the SSD is very defined use case that we can target. And as Andreas and Chris mentioned, the opportunity, like to do it when we start to rank some of the priorities, the concerns, and the business and liability costs associated with not doing it, just it made sense. But yeah, like Chris mentioned, the engine, could be used elsewhere, but the target right now is that use case.
One quick question.
Sorry, I think we're about to switch to our next speaker. So
We're getting cut off.
yeah.
All right.